how can we prevent telomere shortening? This is the thing I was saying you can't do right now, but hopefully we can in the future, with one exception. And the simple, taking into account the fact that our reproductive cells do not age. And we kind of know that because if the theories are right that we age because our cells age, then if all of our cells age, then our children should be born as old as we are. But they're born younger than we are. So that means that our reproductive cells aren't aging. And as it happens, telomere shortening doesn't occur in our reproductive cells. And so this is one of the things that we discovered at Geron Corporation is due to the presence, the production of an enzyme called telomerase. And to explain this cartoon, this is the enzyme that we discovered at Geron Corporation. This is the DNA molecule shown as a double helix right now. Here's the telomere. And telomerase is shown as a factory here. And what it's doing is it's lengthening the telomere. So that's what telomerase does, and it's found only in our reproductive cells. Now, this is a brand new information that just came out. In fact, the paper, this is an announcement that just came in a press release just last night. A paper is going to come out for publication later this afternoon. I have not read it yet, but it's titled "The Genetic Variation in Human Telomerase is Associated with Telomere Length in Ashkenazi Jew centenarians." And what the press releases are saying is that they have found that centenarians have longer telomeres, and they have found that centenarians people older than centenarians have a kind of mutant form of telomerase that is more active. And I don't know exactly what it is yet. The press releases didn't go into any more detail, but I'll have the paper later today if anybody's interested in seeing it. But I think what this is going to say is that people that are producing low levels of telomerase, being hyperactive, better than nothing, no telomerase, are actually extending their lifespans because of telomerase being produced in their cells. Okay, so what telomerase does inside of a cell, we still have the brick layer, and the brick layer is still going to fall off when it reaches the end of this row of bricks. But like an angel, telomerase comes in and replaces that brick. So as a result, during the cell division, the telomeres did not get shorter. And cell division after cell division after cell division, the angel just keeps replacing this brick, and the telomeres don't get shorter.
Is that meant to look like Greta?
Yes. Where's Greta? So, how do we produce telomerase in all of our cells? That's what we're trying to do. And so our simple strategy at Sierra Sciences is to take, we know that somatic cells don't produce telomerase, but our reproductive cells do. Our somatic cells do contain the gene for telomerase. It's just shut off. So our strategy at Sierra Sciences is to figure out a way to turn the telomerase gene back on again. It has to be able to turn on because our reproductive cells have it turned on, so it's clearly something we can do. So here's a basic description of gene expression. In our reproductive cells, there's a gene. This is showing part of the chromosome inside of a cell. There's a gene for telomerase. The telomerase gene produces the telomerase enzyme. Next to every gene in a cell, there's a regulatory element that controls the expression. It's like an on-off switch for like a light switch, or it's also like a toggle switch where you can control the level of how much protein a gene will produce. In our reproductive cells, that regulatory element is turned on. But now in all of our other cells, which we call somatic cells, there's a protein that comes along and binds to that regulatory element, shuts the gene off, shuts the gene off, and that protein is called a repressor protein. What we're trying to do at Sierra Sciences is find a drug that will bind to that repressor, dislodge it from the regulatory element, and allow the gene to turn on. Now, if you decide later you don't want the telomerase gene turned on, you can just quit taking the drug, and the repressor will go back and shut the telomerase gene off again. We call that, therefore, transient expression of telomerase. Okay, and that drug is what we're calling an anti-aging drug. So this is a team of scientists working at Sierra Sciences that's working on this. There's approximately 25 to 30 of us right now. We're located in Reno, Nevada. We've been there for 10 years working on just this one project, nothing else. We have a 10,200 square foot facility, state-of-the-art lab equipment, Very nice environment. I'll explain why in a few minutes. And we have 2 robots that essentially work all the time just screening drugs, looking for drugs that would turn on telomerase. And you can see one robot right here and another robot right here, and right now both of them require a human to run them. And if you look, you can see a robotic arm right there in that red circle. And that robotic arm is what's carrying a microtiter dish that contains like 96 to 384 different drugs that are tested by these robots for telomerase induction. So as of just, I guess that's 3 days ago, we have now screened 161,008 chemicals through this assay, and we have found 33 hits. Now this is, I think, is going to become the biggest thing that ever hit the planet if we can develop these hits into real drugs. And I think this will really change the world. Now, I should say we also have, I'm sorry, that got some slides out of order here. So we have this, the green thing is what our drugs are that we have just discovered, and these are what I'm calling hits. But what I want to say is that we are also working with TA65. TA65 is produced by, it was discovered at Geron Corporation after I left. It is presently distributed by TA Sciences, and they've graciously allowed us to test their drug at our their nutraceutical at our company. And we have been able to show that it does cause cells to produce telomerase. And we're very excited about having the opportunity to work with this. So we have R33 plus TA65, and we're presently continuing to screen 4,000 chemicals per week. So that's where we are. And I should stop here, but there's a lot more to say here. And one is the science is easy. I mean, all of us who are doing science on trying to cure aging, we all know what we're doing. We all have great ideas on how to cure aging. I hope we all succeed. The problem isn't the science. In fact, we have fun doing the science. The problem is the funding. The funding, funding is the obstacle in our work. Now, the heroes in our story are Richard Offerdahl and Pierluigi Zappacosta. They are the major funders for the research that's going on at Sierra Sciences. Neither one of them could be here for this conference, or at least today. Richard Offerdahl will be here on Sunday. We look forward to talking to everybody. He was the president, CEO, and founder of Zycad Corporation, and Pierluigi was the president, CEO, and founder of Logitech, which which first invented the wireless mouse. So these two people are very, very passionate about finding a cure for aging. They and some other investors have presently spent about $27.8 million on our research over the last 10 years. And what we want to do next is, because we have these 33 drugs now, we're ready to start entering a phase which we're calling screening phase 2. And that includes continuing the primary screening. We want to continue the primary screening, looking for more drugs. We also want to do synergy experiments to find out how these drugs work in combination with each other. We want to test other cell lines. Most of the cells we've tested so far have been just fibroblast cells and keratinocytes. We want to do structure-activity relationships called SAR and mechanism of action studies. And we expect that to cost about $30 million over the next 3 years. Then we hope to enter preclinical and clinical research as soon as we have some lead targets. And we estimate that will take $100 million over the next 7 to 12 years. And we think that we'll have a drug available for public use in 10 to 15 years. I call this the cure for aging in 10 to 15 years. But let me qualify that. We have still not shown, and nobody has shown, that replicative aging has anything to do with real aging. So right now, this is just a guess, okay? So the purpose of my company is to really get this question answered. When I started this company, I was afraid I'd wake up 20 years from now and nobody was doing this research. So our focus is to find, in fact, we decided that there's no way to answer this question until we have a drug that turns on telomerase and we can test it. So that's our major focus, is to come up with a drug that we can test, and we feel pretty certain that this will play some role in aging, but we don't know exactly how much. Now, another issue is cancer. And remember, most of my research before Sierra Sciences was cancer research, so I'm very in tune with this subject. And we don't know, and nobody really knows yet, does telomerase activation increase the risk of cancer or decrease the risk of cancer? I'm not going to have a lot of time to talk about this, but I can talk to anybody about it later. We know that 85 to 95% of all cancers express telomerase. But does telomerase cause the cancer, or did telomerase just extend their lifespan, cure their aging? We don't know. We believe, and a lot of literature supports this, that that's what telomerase is doing, it's just extending their lifespan. In fact, most of the literature says that telomerase by itself does not cause cancer. And the literature also says that short telomeres are a major cause of cancer. So when the telomeres get short, our chromosomes become unstable, and chromosome rearrangements and mutations can occur, leading to cancer. Also, when telomeres in our immune cells get short, that can cause our immune cells to lose the ability to fight the cancer. So we have two different ways of proceeding here. Turning on telomerase could prevent cancer by keeping telomeres long, and it also could increase the strength of the immune cell system by keeping telomeres long.